ચારિત્ર વિનાનું ભણતર કશા કામનું ન ગણાય. આપણે સ્વતંત્ર ભારતના નાગરિકો તૈયાર કરવા છે. નોકરી શોધતા લૂલા પાંગળા નથી બનાવવા.
These were the words of the visionary Sardar Vallabh Patel, India's first Deputy Prime Minister and Home Minister. He knew the importance of education and envisioned a thriving ecosystem for rural India, with strong and self-dependent villages, the seeds of which were sown in his hometown, Charottar. As the Sardar focused on the Herculean task of uniting the nation, he handed over the responsibility of developing Charottar into an educational hub to two of its great sons, Shri Bhai Kaka, who was an engineer, and Shri Bhika Bhai Patel, an educationist. Respectfully called the architect of Vallabh Vidyanagar, Bhai Kaka took charge of shaping the dream of a university township. With Bhika Bhai Sahib, they were joined by hundreds of others who devoted their lives to making India's first planned university township. After Sardar's approval in the year 1945, the first blueprints of the Charottar Vidya Mandal and Charottar Gramodhar Sahkari Mandal were drawn up. To break orthodox divides and to bring social changes, promoting secular values, the founders of Vallabh Vidyanagar got a Dalit to inaugurate the brick kiln, a Muslim mechanic to lay the foundation of the workshop, and a Brahmin to lay the first brick of the VP Arts and Science College. Bhai Kaka was appointed the chairman of Charottar Vidya Mandal and continued to lead CVM till 1954. In 1955, Bhai Kaka founded India's first rural university, the Sardar Vallabhbhai Vidyapith, which is known as the Sardar Patel University today. On Bhai Kaka's invitation, Dr. H.M. Patel, a former ICS officer who later served as the Finance Minister and Home Minister, joined the mission as CVM's chairman. He founded new educational programs and placed CVM on India's map. After successfully establishing Vitthal Udyog Nagar, he went on to set up the Charottar Arogya Mandal to support rural healthcare. In April 1994, when the visionary Dr. C.L. Patel took over as the chairman, he took his passionate zeal for innovation to new heights. He pioneered the era of self-financed institutions in Gujarat. He went on to establish a modern-day Takshila, a satellite education township called New Vallabh Vidyanagar. CVM offers a diverse range of programs that include not only liberal arts, commerce, science, engineering, biotechnology, but also home science, law, architecture, Ayurveda, and pharmacy. Institutions like ISTE, GCET, and CERN offer programs for advanced research. Over the past 74 years, CVM has stood out as one of the most unique education hubs that primarily focuses on quality education. The alumni of this glorious institution has reached soaring heights in every corner of the world and has inspired generations. Across space and time, CVM has nurtured the future of more than 10 lakh students since its inception. Today, Charutar Vidya Mandal is the largest educational trust in Gujarat, with 50 plus educational institutions, 30,000 students, 2,100 faculty and staff, making one team. CVM, marching forward. The management team, led by engineer Shri Bhikubhai Patel, is committed to further innovate and work towards achieving the peaks of futuristic learning. Matching the best academic centers of the world, yet encompassing Indian values and cultural ethos, CVM is remolding the face of education in India.
Good morning, everyone. I, Vaidik Vyas, on the behalf of GH Patel College of Engineering and Technology and GCET ISTE Student Chapter, welcomes you all to the webinar Exploring Horizons. It is said that mighty empires are not built in a day. They are outcome of unflinching struggle put forward by stoical people who live there. When you set into a voyage for success, you need a leader to show you a righteous path for the same. We are fortunate enough to have with us our principal, Dr. Himanshu Soni sir. He graduated from Birla Vishwakarma Mahavidyalaya Engineering College in 1997, followed by completing his masters from Birla Institute of Technology, BITS Pilani, by securing the first rank in all postgraduate programs in the year 2003. He completed his Ph.D. in the field of wireless communication from Indian Institute of Technology, IIT Bombay, in the year 2009. He has served as a reviewer of several international journals and as an advisory member of various national and international conferences. He has visited USA, Poland, Greece, Italy, and Japan for various training programs and conferences. He has more than 23 years of experience in field of teaching and research. He has been awarded Research Endowment Prize Award for his research paper published in European Signal Processing Conference, Poland. Currently, he is working as a professor in Electronics and Communication Department and as a principal of GH Patel College of Engineering and Technology. I request you, sir, to kindly introduce GCET to our delegates and participants. Thank you, sir.
Yeah, thank you for nice introduction. Very good morning and warm welcome to all the participants and welcome to Dr. Archana, who is joining from Switzerland Geneva lab, and I'm from CERN lab, and really I'm thankful to Dr. Archana for sparing her valuable time with our students, because in this pandemic time we have to find out alternative means of learning and sharing knowledge. GCET, it is one of the oldest institute in the Gujarat state under self-finance mode, and we are running the different undergraduate and postgraduate program. Along with that, even we are running the research programs, because all doctorate faculty members are guiding the students for their PhD. So that way we are UG, PG and research institute. And in this pandemic time, our all semesters are begin with the online learning through Microsoft Teams platform. And again, this activity is part of our teaching learning activities. So first of all, I'm congratulating the IST team of students and faculties, those who have taken initiative to organize wonderful talk on this weekend. And even really the topic of this talk is very interesting, because see, as an engineer, we all are very well aware about the fact that whatever research we are doing is the applied research. But for doing something which is applied, we need to have a very strong base of the fundamentals. And that fundamental base of research in engineering has been created by physicists, it's been created by different scientists. And I'm really happy that today someone is joining us from the CERN lab, who has worked with very different experiment to find out God's particle. And it was the eye-catching experiment for the whole world, for the all researchers across the science and engineering, to understand that what are the findings. And even we were in touch with one of the scientists in the CERN lab. Even we invited him to our campus just to explore the how that experiment has been carried out. And Alexander Klug was here, madam, with us before few years back in one of the conference. We invited him, Dr. Alexander Klug, and it was really very interesting to see what kind of engineering aspects are involved in the fundamental physics research. So really, we are very happy to learn about that. And again, I'm feeling very happy to see that after 5 to 6 years, again, we have someone who is coming from CERN Lab to delivering talk. And even the topic which has been decided for today's discussion is why sky is blue, and the fundamental research impact on society. So really, it is very interesting topic, not only for engineers, for every person, because all research basically touching to the life of human being. So really, the topic is very interesting. So we are thankful to you, madam. And I'm welcoming all the participants for this talk. And I'm very sure that if you listen the words given by Dr. Archana, definitely it gives you a new directions to understand and to feel the world, because whatever we are doing is we are doing for happiness. So if we know our nature, if we know our motherland, if we know our our cause for the life, which is the nature itself. If we know certain beauties and certain fact about the nature, definitely we feel happy, and we think we change our thought process basically, right? So I'm very sure that all the participants, if they took part actively in this talk, definitely they will learn a new dimensions in their learning phase. And again, I'm congratulating the IST team of students and faculties for taking initiative to organize wonderful event. And without taking much of time, again, I welcome you all to this wonderful event. And now I hand over the session to Dr. Archana. Thank you. Thank you.
Thank you very much for that very kind introduction. And it's so humbling, and even it's a privilege for me to interact with students. You know, I've been one of you, but a long time ago. And this is a good opportunity, a very good privilege, in fact, to be trying to share with you whatever little I have learned ever since I have been in the field. So I would like you all to feel very free to interrupt, to ask questions, or whichever format you wish to take it. When I finish, I can have a Q&A session later on, simply because it's not supposed to be a one-way street. The main point of this whole seminar is to have interactions. And especially in the time of COVID, you all have gathered on the weekend to find time to listen to some of my experiences and some of my thoughts. So clearly, the only fact that I've been at CERN for some time brings me to be able to share with you the experience that I have had and how I feel that India particularly can benefit, and you all can be a part of this whole impact that we are all working towards, the impact towards happiness, like Principal Sir just said. So we are here because all of us are looking for answers to questions to satisfy our curiosity. That exactly is blue sky research. I'm not designing an engine. I'm not designing an aerospace ship, but I am looking for answers to basic curiosity. All of us have grown up, and ever since we were a kid, we wanted to understand where did we come from, what is the world made of, are there other universes out there? I'm sure many of you, like me, were lying in your bed looking at the sky in summer particularly and wondering what is out there and what is beyond. And while we are looking for answers, we are able to design experiments, and these answers have given a very huge impact to mankind. That is well known to you. And these are some of the stellar scientists from our country. I do not need to introduce any one of them to you, but I'm sure you can imagine the impact that they have had on science and the impact that they have had on society, particularly in India. So I have been fortunate. I actually had a, let's say on paper, quite a stellar career in terms of having marks in my school and my college and so on. However, working with stalwarts like Nobel Prize winners is a very big edge that one can get in life. So there I was very lucky, very fortunate that I wormed and worked a lot, and I was picked up to work with Professor George Sharpak, who was the group leader where I came to CERN. And these are some of the other prize winners at CERN in my field, that is high energy physics. Again, what is common between us and them and all the other people I have just showed you is that they have been curiosity driven in search of answers to the questions that could have an impact to mankind. However, they are not looking for that impact. They are just looking for answers to questions. And we all are standing, as you know, on the shoulders of giants. This picture is very well known to all of you. You have studied in your school or college, rather. And this is a sketch of Newton asking a question, why did the apple fall down? And of course, he did not stop there. he had this aha moment when he said, if the apple falls down to the earth, and that's the reason why the moon does not fall down to the earth. It is in an orbit. It's held in an orbit because of some force. Similarly, the Earth itself is held in an orbit around the sun. And these were the questions just because he asked himself, why did the apple fall down? Or why does not the moon fall down? So these are answers. But then from gravity, we have understood, of course, the famous laws that you know of, and of course, how the whole solar system goes about its journey and how we can exist on Earth. We have understood the Newton's laws of motion. We have understood eventually how the cosmos works, how the galaxies move, and all this is standing on shoulders of big giants like Newton. And you also heard about the gravitational waves. That was in 2015 when the announcement was made of two black holes colliding, and the gravitational waves that were observed on the Earth with very sophisticated instruments. And of course, today we do not know what this is going to bring to us. But very soon we understand the impact that this will make to society. You've all learned of these equations in your classes. I will not go too much into it because you are, as engineers or budding engineers, you are well aware of the impact that these equations have had on our lives. In every instrument that you touch today, or just at every fingertip of usage of any mobile phone or a laptop or any other instruments and equipments around you, these equations play a vital role. And of course, you know that, all the people that were behind over there. There was Maxwell, there's Hertz, and the whole series, of course, of giants on whom we are standing, on the shoulders of whom we are standing. Einstein, how can we miss, speaking of Einstein, without and move to anything else? You all know about Einstein and his photoelectric effect, his theory, his work on theoretical physics, his work on Brownian motion, trying to explain that. And of course, all these are not just concepts. All of you know that this very famous equation, one of the very famous equations, apart from E is equal to mc squared, that tells us and helps us to calibrate our GPS. And the GPS satellite clock advances faster than a clock on the ground by about 38 microseconds per day. So we would not be able to move around the way we do today, because in a moment we quickly go on Google Maps or any other application by which we are able now to get more and more dependent on finding our way in the streets or in towns where we need to go. Now, this is just to tell you that when Einstein was thinking of explaining the dynamics of the Brownian motion, he obviously was not thinking of the stock market, or he was not thinking of the financial and risk analysis. However, the microscopic dynamics of particle collisions, which then explained the macroscopic dynamics of the Brownian motion, which was a very big contribution from Einstein, is actually the same model, which is the financial Brownian motion model. And you can look up several works that have been done in this direction. You can just look at where the physicists disappear. After they graduate, 80% of them go in the financial and banking sector, simply because of the fact that the tools they have learned and the techniques that they have learned, the algorithms that they have learned are directly used into the financial markets. So yes, now we just look quickly at one or two more concepts before we dive into some other things. Bose-Einstein statistics, you have all studied, and you know about the fact in Mumbai, these are the trains of Mumbai. Can you add one more person there? It's kind of difficult, isn't it? So these are the fermions, where each person or each particle, so to speak, occupies one unique place, which means one unique quantum number. And if I go into a similar train, which is represented by this shape over here, and I add a lot of ghosts here, I can add as many as possible. So it means that they do not need to be defined by a unique quantum number, so to speak, which means that we can stuff as many as we want, those kind of particles that are called bosons, as many as possible in the same place, in the same. So many of them can be identical in terms of occupying the parameter of the phase space where they are stuck together. So these are the two ways in which particles exist in the world, and that they are fermions and bosons. And I've heard about Satyendranath Bose, and you've heard, of course, about Fermi, and together they have given us the Bose-Einstein statistics. And of course, the quantum mechanics sounds very complicated, but it's not. It just explains to us how atoms can be made, how molecules can be made, and eventually it explains to us how we are able to understand the universe. So yes, in the same theory, when we continue this journey of a bit of a historic evolution, you know very well all the kind of things or utilities that we use in our daily lives, in hospitals and in airports, and wherever you go, you are using these kind of instruments. At home, you are changing channels by just using simple lasers, right? So these lasers are made just by adding photons, and again, they are based on the statistics that was developed earlier, right? So yes, we will now try to go just one more chapter here, small one, which is about the electrons. Little did Sir J.J. Thomson know that when he discovered the electron, what exactly is going to follow, something like an electronics revolution, or mega revolution, I would say, which has completely changed the face of society, so to speak. It's fantastic to see, dudwalas operating their mobile phones, and in the villages as well, everyone is able to watch their televisions and so on. So it's just incredible the way something that happened more than 100 years ago, and how society has been impacted. Similarly, you know about Röntgen, who had made the first X-ray of his wife's hand, and today how this is an important tool in every hospital, or for every in my arthritic bones, for example. When I need to get an X-ray, I just go and I assume that the doctor will be able to look through my hand, but somebody was working in this direction. However, he did not know, but we know. So blue sky research essentially is a one-way conversation. So we are able to speak to Sir J.J. Thomson, but he is not able to speak to us. And that exactly is what we speak about blue sky research. Now, why is it so very important? Just look at the situation today. Where are we today? We are in a pandemic situation, a translational global pandemic where millions of lives are being affected. Now, if we were to look with a visible light microscope, we would be able to not see very carefully the coronavirus. And why? Because the resolution of the visible light microscope is about 200 nanometers because of the diffraction patterns of light. However, when you go with an electron microscope, a scanning electron microscope, you are able to get a fantastic close-up of the coronavirus. And similarly, the tools of computing help us to simulate the properties. And that is exactly how we will be able to learn about the virus, and then we will be able to find a vaccine only when we understand what is the enemy exactly. So I hope that I have shown you that blue sky research is incredible. Today, the whole world is looking at scientists to figure out some way out from this pandemic. And this has come about because of curiosity to understand the constituents of matter. All of you, of course, know this picture very well. I think I do not need to spend any time here except to come to the end, which is that an atomic nucleus is made out of protons and neutrons, which are very tiny, and they are also called collectively hadrons, just for the fact that they have an interaction called strong interaction, which you also would know, I suppose. And the electron that goes around the nucleus is a family called the leptons, light particles. And the proton and the neutrons are made up of quarks, and there are different kinds of quarks. How do we know this? Because we have been doing some experiments. We are smashing things together, and we are then able to see what happens after we smash things together. So let's play a little game. Let's take two helicopters made out of Legos. All of us have played with Legos, right? So they are little units, and we put them together and we make some helicopters. So let's start to see what happens. Boom. And with a little energy, they break into different pieces. But you can surely see that they are not the fundamental pieces. They are still bigger pieces. So these kind of experiments have been done in laboratories. These kind of experiments have been done in balloons, where, you know, in the balloons have been sent up high in the sky, and in the atmosphere you have the cosmic rays, and these cosmic rays, they then strike the molecules of photographic plates that are kept inside the balloons, and they are then analyzed. So then we are able to look at the collisions that have happened by cosmic rays, which are protons and pions and other things, which then result in tracks, which we are able to see these on the photographic plates. So it all depends on the collision energy. I will have to increase the collision energy to be able to see, can we go to the fundamental constituents? And indeed, that happened when we increased the collision energy. So now we have understood how to make an atom, and let's make a helium atom. So we take protons that are made out of quarks, two up quarks and one down quark, and we have electrons, and we have the neutrons that are made of two down quarks and one up quark. And let's put them together. We've got a helium nucleus, we add two electrons, and then we know how the helium atom is made, which means that we understood exactly how to make all atoms of the periodic table, correct? So we have fundamental particles called quarks and leptons, and we are able to make the whole universe. So studying fundamental science from the atoms and the way it behaves, what are the forces that exist between these particles, we got a lot of results in terms of applications. And particularly for engineers and budding engineers like you can see and even imagine way beyond what is represented on this slide, because we have food on our table, because ships and aircrafts can move. We are able to go into space and perhaps harness a lot of returns once we are able to maybe colonize perhaps space later on. And of course, all the dreams like, speed cars or toy cars, we are able to predict the climate because we are able to use computation. We are able to do many, many things, of course. So now let's say a quick summary. Electromagnetism that holds the atoms together, that gives us light, that gives us the radio waves. We have strong nuclear force that holds the nuclei together. We have the weak nuclear force that gives us radioactivity, and together they make the sunshine. And we exist because the sun shines and the earth goes around the sun, and we have our day and night. We have the warmth coming from the sun as well. So we exist. So we understood our existence. We understood the planet, the solar system, and eventually the whole universe. So now let's start asking some more further questions. Where did we come from? So you all have heard about the Big Bang, 14.7 billion years ago. And this, if we continue the game of collisions and trying to understand where did we come from, the kind of energies that happened at the time of the Big Bang is where we need to get to be able to know what were the particles, how are these particles made, what was before that, and so on. So questions will continue in your mind, and I'm sure they are bubbling already now. So essentially 10 to the minus 43 seconds later, the temperature was 10 to the 32 degrees, million times than in the heart of the sun. 10 to the minus 34 seconds, you see energy starts converting into some kind of particles. And that's where we are interested in. We need to know what are these basic particles. Again, 10 to the minus 10 to 10 to the minus 5 seconds, quarks start appearing. And then eventually there is between 3 minutes, just after 3 minutes, we are able to see the first atoms. So these are the processes which we try to study in particle physics, how this whole thing came about, and what exactly happened to the antimatter, by the way. Because we are here, it means that when the Big Bang happened, matter and antimatter, in principle, should have been created in equal amounts, right? However, this didn't happen. We were in excess, so the matter was a little bit in excess, and that's why we are here. So these are kind of questions that we are still studying. And of course, the cooling is continuing. We are at 3 degrees Kelvin in outer space, and we are here at this point reflecting on how the universe and the galaxies came about. Questions again, more questions for this blue sky research that's being conducted. What is the origin of mass? So from the energy that was bubbling in the very early time of the universe, how did particles get mass? Why is the proton so heavy as compared to the electron? And you have heard about dark matter probably, because 95% of matter is not known. We can only account for 5%, which means what is this dark matter? Is it matter at all? Is it another form? We have no idea. So in our experiments, we are looking for signatures if we can find some new state of matter. Matter versus antimatter, I already mentioned to you. And this primordial plasma, or the soup, the cosmic soup that was created just after the Big Bang, is what we want to study. So to look for these answers, I think I have demonstrated that these answers are going to impact millions, if not billions of lives. And that the experiments that we want to do are called collider experiments, where we are going to do these collisions of the helicopters and, of course, with protons then. So let me just do a quick summary here. We have understood that there are two families here, which means the up quark, the down quark, the charm, the top, strange, and bottom, which together make 6 quarks as the fundamental particles, the fermions here. Leptons, the electron, the muon, the tau, which comes with its own neutrino as well, these are the leptons, right? So together, these are the fermions, and they come in 3 generations, right? So first, second, and third. Force carriers. How does electromagnetism happen or magnetism happen? You know that when you are holding 2 magnets, they are talking to each other. If the opposite poles are there is no way you can get them together, right? On the other hand, that they will be attracted very, very strongly. But if they are 2 north poles, it's very difficult to get them together. So what is there between them? So these force carriers are called bosons. These are the gauge bosons. And for the weak force, they are W boson and Z boson. For the electromagnetic force, it's the photon, as you know. And for the strong nuclear force, it's the gluon. And here you see that there is another particle that's called the Higgs boson, which actually is the mass-giving boson. And that is what was not observed until a long time. In 1964, this question was, of course, bothering the scientists from a long time. And these people, all of these very august people here, Kibble, Guralnik, Hagen, Engler, Brout, and Higgs, they proposed a theory which is now called the Brout-Engler-Higgs field, and they explained to us that the whole universe is filled up with another field. Just like the magnetic field, there is a Higgs field, okay? And this field is responsible to give mass to every particle. Now, this field is obviously invisible, otherwise we would see it. So how can we prove it exists? So let's try to do some more experiments. Let's increase the energy of our helicopters. And we all know one equation which we can never forget from Einstein, that is E is equal to mc squared. And after we increase the energy, what happened? This is very strange. We didn't get any more the Legos, right? We did not get any more the individual particles. But what do we get? We get in here an analogy, of course, dinosaurs. Do we believe in dinosaurs? Yes, of course. Why? Because we have seen the remains, we have seen fossils, we have seen footprints, we have seen many things, right? So similarly, but we know that they do not exist anymore. Similarly, there could be particles that did exist at the time of the Big Bang in the cosmic soup, and they do not exist anymore freely going around, right? So we need to increase the energy of our accelerators and do these experiments, right? So now we want to do this experiment. It is unfortunately very, very, very expensive to do these experiments, which is why countries have to come together and then make laboratories like the CERN laboratory, where we are going to collide proton beams inside accelerators and create particles that existed at the beginning of the universe. So we will not only create the dinosaur particles, but we will create unexpected particles. We have no idea. We might create dark matter particles, right? And of course, we might also create the Higgs, because that is the target. We know from the theory, from the mathematical formulation, we know that we are able to have mass given to all the standard model that I showed you of particles. All particles can get mass when they interact with this Higgs field. So the Higgs boson is very heavy, 100 times. This is what was predicted. We did not know the exact mass, but we know that it was very heavy. And it is also very rare. And also it doesn't hang around. It just decays instantly into other particles. So how can we detect it? We actually found it despite all these difficulties. So how do we go about it? First, we need to make our accelerator, which are these powerful machines that can accelerate particles to very high energies and then bring them into collisions. Then we need to take pictures of these collisions. And these pictures, we need to take a huge number of pictures, because statistically we can get one Higgs boson only when we have a huge amount of data, right? So we have to take pictures 40 million times in 1 second. And then when we collect data over months and months, we might see the Higgs boson. We need a lot of computing power, because we need to collect all this data, we need to analyze the data, and then we have to distribute it as well, because the amount of data that is created in these experiments is of the order of petabytes. And it's not simple that one computing center or one tier, so to speak, is able to manage. So this is called distributed computing, which I will speak about later on. And of course, it cannot be done by one university, one institution alone. And this is the power of collaborative science. So thousands of engineers, scientists, and technicians, students, and support staff build and operate these complex machines. So here you see, this is Geneva, Switzerland, an aerial view. And this is the airport. My house is close by over here. So I'm right here if you want to place me somewhere. And you see, this is the universe ruler, where that's the Big Bang, and that's where we are in the universe in terms of scale. So this circumference that you see of a footprint of the Large Hadron Collider, so to speak, that's the name of the collider I'm going to speak about, is 27 kilometers. It's a huge area, right? It's a huge surface over which this experiment is built underground. And what you see in blue and red are the proton bunches that go around 8,000 times in 1 second, and then they collide in different places where you have these experiments. And exactly this renders the Large Hadron Collider as if it is a super microscope, and we are able to look inside matter. That's a picture of the accelerating tunnel. So that's the one of the magnets. You see the two beams here, and the vacuum inside the beam is very, very high, which means of the order of 10 to the minus 10, 10 to the minus 11 torr. It's better than that on the moon. And of course, these it's a 54-kilometer fridge, which operates at 1.9 degree Kelvin. And the beams, these proton beams, they are running at energies which are very, very high. And at the moment, they are 3.5 on 3.5 TeV. And then eventually we went to 6.5 TeV, which means 13 TeV as such. So this machine is an extraordinary machine. It's working on superconducting magnets, which operate, as I said, at 1.9 degree Kelvin above zero. And the vacuum is incredible. To maintain this vacuum is incredible as well. And of course, it has to deal with temperatures that are 1 billion times that in the center of the sun. So imagine the engineering that goes behind it, the material selection that goes behind it, the currents that are needed to operate these magnets are of the order of 20 kiloamps. We are underground with our experiments. The protons, they are circulating. And that's the surface. It's just, again, to place you where we stand in terms of, two countries, first of all. So on the right is Switzerland, on the left is France, and my experiment is right there, CMS, where I work. Okay, so these are the two large detectors or experiments, so to speak, because they contain many, many different kinds of detectors. There are two experiments because they are competing with each other in a very healthy and collaborative manner, so that if something is discovered by one, it must be discovered by the other one as well. There are various technologies that are used in terms of making these detectors, because different types of particles are coming out. Some are neutral, some lose energy very close to the interaction point, some traverse the whole detector, and so there are different sensitive layers in these experiments. And this is so-called compact muon solenoid, and this is the ATLAS experiment. It's like a 6-storied building, and every piece of the building is a sensor. Similarly, in CMS, it is compact because it has a magnet which is very strong, 4 Tesla magnet, and the weight of this whole experiment is 14,500 tons. So it is a very, very sophisticated detector. There is a pixel and tracker detector. This is made out of silicon. You have electromagnetic calorimeter, and you can read about it more when you look on some pictures of the cavern where we work. You see, these are some of my colleagues. They are working on repairing something. You see, this is the beam pipe in the experiment. Here, one of the pieces of CMS is being lowered from the shaft. Each piece is very heavy, as I mentioned earlier. And this is, if I remember well, around 2,000 tons. And that's me who's actually recently we have upgraded part of CMS, and that's one of the detectors that I have helped to design and install. Now, looking at the data, I mentioned that this is huge amount of data we are talking about. So we need to understand the computing algorithms and how we are going to share the computing load. And CERN has only 20% of the capacity, and that gives rise to grid computing, which you may have heard about as well. And India also participates. India has 2 tier 2 centers and several tier 3 centers. So we participate in all these experiments in a very big way. So you have also probably heard that CPU scaling has come to an end. Now we have to move to GPU scaling, which means, graphic processing units have to be used, because now we have to move from petabytes to exabytes in the future. We need all sorts of tools that are needed in terms of neural networks for doing our analysis. We need machine learning. And of course, these are the tools that are learned by young students who then go out in the world and make big differences in various social arenas. So this is a collision between the protons, and what is coming out is 2 photons, which means that this could be a Higgs. Our theories tell us that when 2 protons collide and when a Higgs is made, then we would see 2 photons. So this was indeed found in the Large Hadron Collider. And what you see here, a lot of background is there, and this background needs to be subtracted. Only then you see a little bump here. And this bump was seen not only in ATLAS, or it was also seen in CMS. And there were other modes of decay also of the Higgs that were seen. And this was incredible that both experiments saw the three different signatures in a very sharp manner in a discovery mode in 2012 in summer. So this was amazing. There was a big seminar that happened at CERN on July 4th, 2012. And I didn't get a place to enter there in this big hall here in the conference room at CERN. I came at 5 o'clock in the morning, but still I was not able to find a place because people were waiting with long queues outside. This seminar was the historic announcement of the Higgs boson, the so-called God particle, by CMS and Atlas. And it was a live broadcast to Melbourne in Australia because there was this big conference going on. And of course, it was caught by all the media in the world. And it was incredible that Professor Higgs, and the whole team who had given us the Higgs in the form of an equation in 1964, 50 years later or so, it was found in the CMS and Atlas experiment. And on Tuesday, 8th of October, the announcement was made for the Nobel Prize for Francois Englert and Peter Higgs. Here we had a big celebration at CERN, of course. And then the Nobel Prize was given in December to Peter Higgs and Francois Englert. All right. And of course, there is a big team of CMS India that is working in India. So any of you who are fired up to do any work in terms of making detectors or working in the future, you have a lot of anchors where you can go and find information and internships and so on over there. Now we are busy studying the Higgs and trying to understand what more. Shall we look at the dark matter particles? I hope that something comes out in the next runs that are coming up, and then in the upgrades of the LHC that are happening soon. So we have to understand now how the Higgs behave and how are there other Higgses as well and so on. So there are many other kind of questions. So you have certainly, you will agree with me that we have to continue this kind of blue sky research because nobody was imagining what's going to come to the society while we are looking at answering those questions. But then accelerating particle beams, detecting particles, and the large-scale computing grid have given phenomenal contribution to science, to the society. Let us take one example, and that is hadron therapy. So hadron, you remember, that's protons or other particles that are strongly interacting, and we can even have ions nowadays, where we accelerate these particle beams with the techniques that have been now devised for our experiments. But when we use them for radiation therapy, as you know, for cancer, when we use X-rays, we damage a lot of the healthy tissues as well, because it's like shining a torch in the body. And you have other organs, sensitive organs like the brain or the heart or the lungs or the kidneys. You could potentially damage the healthy tissues. So there is always collateral damage to the patients. And typically, the quality of life of a cancer patient is much reduced because of this collateral damage. But when you use protons or hadrons or ions, one is able to deposit the energy and kill only the tumor, or you can come to millimeter close to making a digital scalpel and just addressing the tumor. And this technique has been now commercialized, and more than half of the accelerators in the world are used for medicine. And in Europe and USA, this is very advanced, and many facilities are already there. Similarly, doesn't this PET scanner, positron emission tomography, look like one of our detectors? It is indeed a detector converted into a scanner, and there is a business of superconducting magnets of 2.4 billion, by the way, for hadron therapy and PET scanners together, that form the computed, computer tomography for cancer, for imaging, for Alzheimer's disease, and of course for doing all the kind of patient treatment methodologies that are used for those treatments. Just a very quick reminder of the little detectors that are sitting in CMS. These are silicon layers that have been looking for the Higgs boson and looking at our collisions, and the very same detectors can make images like these of a flower. So it means that if we continue to do the work in this direction, we are able to look inside the body to a degree that is a doctor's dream. And the contrast is incredible, as you can see here, between the tissues, and you are able to recognize the features in a very sharp manner. This, if you have seen this picture, probably yes, because it was flashed a lot in the media, and this has been viewed over 40 million times on Twitter. So indeed, the first color X-rays have been done using the detectors like the ones I showed you before. And this is another dream of a doctor, where the doctor is able to look at the bones in great detail inside an ankle. And people with arthritis, or people with other injuries or osteoarthritis and so on, or just to look inside the body. This is just an example where these detectors are able to be employed. Health safety when you are flying, because the pilots, for example, are exposed to radiation. So how to monitor that is what is being done using detectors as well. You all, of course, use the World Wide Web, www, and I hope that you all know that this was developed at CERN when physicists wanted to share data, and Sir Tim Berners-Lee, who was just a young student at that time in the early 20s, he proposed the HTTP to his boss, and the boss said, vague but exciting. That was blue sky. He had little idea what the world is going to happen after the World Wide Web is given to the world for free. And today, internet boasts of trillions of dollars of economy, and the GDPs of countries to a certain fraction are based on the internet. Pandemic fighting, all data sharing, policymakers go directly to the web and try to understand the data from various countries and try to understand how we can do best, right? Similarly, this is used in many other fields, for example, in bioinformatics, in genome sequencing as well, for education and training. I mean, you all are engineers, and I can tell you that when I learned the movement of pistons in terms of equations, and the problems were given by my mathematics teacher in my B.Sc days, I could solve the equations all right, but I could never imagine visually the piston movements, right? And put every piece together on how this equation is gonna dictate the movement of this piece or this gear of the whole machines. So today you can visualize these things, and today the whole education and outreach has completely become a level playing field. If there is any student who wants to learn something, you just go and Google, and there you are with like hundreds of resources from where you can learn. The meteor forecasting has become so accurate in the world just by using distributed computing, and money and human lives can be saved, just like in India also, for example, the cyclones and hurricanes and other disasters can be averted in terms of saving money and human lives by accurate weather forecasting. There are many other research programs going on at CERN. I will obviously not be able to go into that detail, but you are all welcome to browse on the website of CERN to see the kind of exciting vistas that we have. Just a quick example of how a young student who came to CERN for a short while, and she learned the techniques of analysis, of data analysis, data crunching, and so on. And the moment the pandemic came, she was able to make a little app of tracking the temperature of the human body. And though this app was then very useful for fertility and COVID-19 tracking. So this is incredible. And I think now she's a millionaire just because the connection from the God Particle Laboratory into a market-based app which is now running all over the world. And I think it is wise if you look into the lessons that are taught just by the fact that in 1 year of whatever she learned, she was able to completely harvest that back into and plow it back into society. These are just examples of how everyone in the world is fighting against COVID, India included. As you know, ventilators are a big thing now because of the lack of ventilators in our country. I mean, I do not know the exact numbers today, but when I had prepared this, there were 40,000 ventilators. I think the number has doubled by now. And of course, at CERN also there are many innovations of different kinds of ventilators, and you are welcome to take a look there on what has been happening. This all, whatever I have recited to you, is now telling you how is it possible? How is it possible this amazing, huge impact of research over decades, continued research over decades? This can happen only when we work in a collaboration. Everyone is very useful, and every person makes a contribution, whether it's a small student, young student, or the senior person who has the ideas, and so on. So I let you think about the fact and reflect of the fact that how large collaborations can really be very successful simply because of the clarity of how we work together and how every cog in this big giant wheel works together. So looking at the future, just a very quick look at the next big project that's coming up. That's the Future Circular Collider. It's going to be 100 kilometers in circumference. And of course, these will address future questions on blue sky research. This whole thing is going to be operational in 2040. So it's really up to the younger generation of engineers and software specialists, physicists, experimentalists who are going to take this forward. So the idea really is to look at mega science, blue sky research, and see what are the technologies that are being used over there. And these technologies can directly be translated into many fields for the societal benefits. Medical, biomedical technologies. I have just given you a window. You have to go jump in there and then look around what are the various fields which interest you, because this is, each one of these pieces that is written over here can be a seminar in itself. So I invite you to take a look. All this is given on kt.cern pages, web pages at CERN. All right. Many applications, Internet of Things, machine to man to machine, and so on. There are so many things that can be interesting. So do take a look at kt.cern. So yeah, I mean, like me, and I am still in the same phase, because the more you learn, the more you know how less you know, right? So you keep moving ahead. You try to understand, do I want to take part? Do I want to learn? Do I want to engage? And eventually, as I showed you, the projects of the future are incredible. And maybe you, some among you, is going to be leading these projects in the future. So with those kind of thoughts, I run a foundation. That's a 4-year-old foundation. However, I was working haphazardly before that. Now it is a bit more coordinated, where we have many students whom we work together with, and we are trying to form them. We are trying to do a lot of outreach and so on. So the lesson is that particle physicists can essentially do everything. And if I can work on this, anybody can work on this as well. So this picture is a bit complex, but it just shows you the whole story that I have just told you. You start with a question in a creative period where you make a little sensor, small one in the lab first, and then huge, thousands of meters squared in the experiments, taking data, crunching data, maybe run away after doing your PhD, or maybe even just with a year of experience, you run away into financial or risk management. You do a lot of engineering, you go into space applications, astrophysics, medical physics, industrial and safety applications. You can go into environment, meteorology, you can be doing outreach. And of course, the biggest of it all, the master, is the science project management. Today, it's a very big field, and we need to have huge amount of experience to be able to do it properly, because these projects are decades long, and they and they are very, very expensive as well. So here I'm going to stop and then maybe take questions. Thank you very much. I hope you're still there. Hello.
Yes, ma'am. We are almost ready with the number of questions which are raised by the audience. One volunteer from the student team will be ready with the Q&A section.
Thank you.
Good morning, ma'am. So basically, we have collected some questions already from the participants. And the first question is, considering the open-ended nature of fields in blue sky research, how do you decide upon which field to choose? Its surety of being helpful to society in future and grant provided considering it may take forever to complete the research.
So I think the best way to move in this is, first of all, what interests you, because interest is very important. And I would suggest that if there is a field that is of interest, because I remember when I was young like you, it was not easy to understand what interests me, because everything was so interesting. So the best way to do is to go and grab an internship in the field which interests you, and if you can find a good mentor in that field, I think that's the way you can move ahead. The internship will also tell you if you do not want to go in that field. So the best way is to keep experimenting as much as possible, talk to people, talk to potential mentors, and then you will certainly find one place where this will click if you are really interested.
Thank you, ma'am. And there's another question, that is, can you provide one or two recent examples of how the blue sky research done in past is impacting the nowadays life?
Okay, I think I explained a lot in my talk about this. Today you are listening to me simply because of the way we are able to use and exploit all the electronics, all the bandwidth, all the communication tools, right? Google Meet, it's over the web. The World Wide Web was invented at CERN, as you know. So there are, I think, everywhere you look today, there is an impact of the work that is done in the past.
Thank you, ma'am. The further question is energy of light more than the energy of newborn black hole?
Well, I cannot say exactly. I didn't understand the question. Energy of light. I mean, a black hole has no. A black hole as such. First of all, I have to admit I am not an expert in this subject. But when a black hole is born, then the energy is very different. We do not know about it, and we are actually trying to study that. So one has to first study a bit more on this subject, and then we will be able to give answers.
So, ma'am, there's a question in the chat box by
Yeah.
Parthe sir.
I really cannot answer this question. I'm sorry. Alternate current, that one? Disinfect, because I do not know the connection of the biology of this frequency of AC current. I am afraid I cannot answer this question. Sorry. disinfection. I mean, I will read about it. It's very interesting, and I'll definitely try to understand better about this. Where is the statement coming from, I wonder? So are there any more questions? Otherwise, we can close the session.
No, ma'am, there are further more questions coming up in the live chat. So the next question is that, just a second, yeah, here it is. Yeah. Do you feel that one day technology would reach at its peak and there will be not any further development?
Okay, you know that when in 1937, IBM's chairperson said that I think in the world there is use for probably one computer. That's what he said in 1937. I think in the 70s, again, when Microsoft started making its computers, that maybe 4 or 5 computers will be used in the world. So see today where we are. Similarly, this is a story in every field. We do not know what's coming ahead. And that's the importance of remaining open to the unknown unknowns. We know certain things, and those things are going to guide us. Those technologies are going to guide us. I can tell you that my grandfather would have been completely not believing me when I would tell him that I can speak on a phone without any cords or without any cables to someone in New York. He would not believe me, I'm telling you. And it's the same story today. There are so many things which we do not believe. We could not believe that we could go to Mars one day. And who knows what's coming in the future? So one should always remain open. And there is also another theory about what could be invented has been invented. These are also stories that we hear. But every time you have new inventions and new vistas are opened and new questions also come along. So again, it's back to the loop between blue sky research and what comes back in terms of technologies and what can then impact society, right?
Yes, thank you, ma'am. And there's another question from Dr. Mehul Shah. That is how Indian rishis have predicted so many things about universe without building big laboratories.
Okay, so let's take some examples. It's not only about building laboratories, but I think that there is, of course, a lot of heritage that we have in terms of science in India. And a lot of it is not documented, so to speak, but there is a lot of scientific corroboration and work is happening in this direction. For example, you know, the Ram Setu between India and Sri Lanka, you know, this was eventually found and calculated in terms of the sea levels at the time of when the Ramayana actually happened. Those sea levels were low and people could walk from India to Sri Lanka. This has been documented. So the knowledge of, let's say, the thought experiments is definitely very important, and it continues until today. I mean, Einstein did all his work in thought experiments. He did not have any laboratory. So I think that there is ample proof in today's theoretical physics world where a lot of the work is done through thought, through mathematics, and our, let's say, bad luck is that we do not have a lot of that work documented. If it was documented, probably we would have had groundbreaking discoveries already much earlier in our own country. And I think we are improving a lot, and there's lots more to do in that direction.
The further question is asked by Virat. Ma'am, is it true that in a stable state of matter, it seems to create a kind of portal, which possibly allows for time travel?
God, we have to wait and see, I would say. That's the answer, because you have heard certainly about string theories, you have heard about entanglement, you have heard about the fact that for quantum computing, you know that a photon here can be connected to a photon millions of miles away, and so on. So, time travel, unfortunately, how I understand, is only in one direction, because that's why we are here. From the Big Bang, we are only moving in one direction. But it's still beyond my capacity to fathom and to understand how we will be able to go backwards in time in the spirit of how we understand it today. Maybe that there will be a better understanding or an improved understanding of time travel. We will know when these experiments will be formed in real time, when the SpaceX will launch us somewhere else, and we will try to see if my twin in another planet is going to age faster than me. Those kind of experiments will be done. It's quite mind-boggling, and eventually I hope that some answers will come eventually.
Okay. There's a question from Malhar Suthar that is space a superfluid?
Superfluid. I think space is made up of a lot of things that we do not know, like dark matter and dark energy. So I can only stick to saying what I know, and what we do not know is what we call dark energy and dark matter. We do not understand which is the state of matter. So I will not try to correlate that with superfluid or something. There could be spaces, there could be stars, neutron stars, and so on, where there could be a state of superfluids in the various state of matter over there. But in general, we could not make a general statement.
Thank you, ma'am. The other question is, ma'am, can you please put some views on the field of cosmology as a career?
Definitely. There are many, many experiments studying cosmic wave backgrounds, and there are many experiments, large experiments also, where India is participating, like the 30-meter telescope, and there is the square kilometer array. There are many, many experiments, and I think there is a huge potential of becoming a cosmologist.
Okay, the next question is by Sujal Lukhani, that do you believe in black hole theory or eternally collapsing object, and why?
So these are things which we need to understand better. I mean, the understanding is coming very slowly. We do not know. There are, multiverses out there, or what kind of, are we alone in the universe, or there is going to be a lot of speculation at the moment. And I think that the people who are the theoretical physicists who are looking at these questions, remember that I am a nuts and bolts physicist. I work with detectors, and the little I know is in that field. So please don't challenge me too much with the questions on these kind of black holes and gravitation and all that, right? I will send you to my experts. I will suggest to you to call some other people who will answer these questions much better.
Thank you. How can we, the next question is, how can we know that the path we have chosen is right? Because at some point, we can get confused. So what are the, like when you took up this whole CERN thing, and then how did you know, like, yes, I'm fit for it?
Yeah, it will never happen, because we always feel like an imposter, and students particularly, I mean, whenever you start your careers, that's how things happen, that, at least for me, it was true, where you always have this imposter syndrome. You think that you are not good enough, you do not know enough, and so on. But on the end of the day, you continuously keep learning, keep doing whatever best you can. And I think it's the best way to always remain learnable, so to speak. Nobody knows everything, and one learns something from every interaction. So today also I'm getting to learn. I'm learning the questions I do not have answers to, so I'm going to learn about those questions for the next talk, and so on. So I think we have to just continuously learn and never treat any sort of failure as a failure, because a failure is a learning opportunity, right? So the moment you change your gear in your mind, that okay, fine, I didn't know this, or this, I failed here, what a fantastic opportunity that it has given me to learn and to move forward. So just change in here about the way you learn, the way you move ahead, and continuously build upon every single day is an opportunity.
Thank you, ma'am.
Okay, so I think we have
The best things in the world cannot be touched or seen, and thank you is one of them. I, Sakshi Patel, Vice Chairperson of GCET ISTE Student Chapter, consider it a great privilege to propose the vote of thanks. On behalf of GCET ISTE Student Chapter, I would like to thank G.H. Patel College of Engineering and Technology, a constituent college of CDM University. I would like to thank Dr. Archana Sharma, Principal Scientist, Geneva, Switzerland, for giving her valuable time. We have been fortunate enough to have been backed up by a team of dedicated volunteers. Thank you so much. Lastly, I would like to thank the participants without whom the event would have not been successful. I would like to call upon Professor Parthish Makodi sir to say a few words.
Yes, thank you, Shakshi, for the good vote of thanks, and especially thanks to our today's speaker, and hats off to you, Dr. Archana Madam. We also do organize the TEDx talks in our campus, and we are delighted to know that you are also one of the TEDx speakers. But I must say, if you have been invited to give the TEDx talk, your session is as good as 3 TEDx talks today. The plethora of applications of engineering and science you covered in the today's session, that is much appreciated. There were so many questions in the young minds, right? And we were able to justify it in a proper manner. Due to the present situation, we were able to meet virtually through this platform. And we are thankful to all our technological inventions so that while sitting in the different continents, we can address the student community together. Thank you very much.
Thank you very much. And this is really an invitation rather than a speech. It's an invitation to you to go around, look around, and learn more, because learning to learn is the biggest tool I have learned.
Yes, ma'am. At the end, I would like to request you to, give some light about the NGO with whom you are associated with, if you can,
Sure. Certainly. I mean, the website is called lifelab.org.in. And you can Google it up. There, what we are trying to do is we try to do a hands-on experiment. Now, COVID has completely blocked us, but nevertheless, we try to have interactions with experts. We try to train teachers with 21st century pedagogic values. Let me tell you something that here in Switzerland and in Europe in general, when the Higgs boson was discovered, within a couple of years, it was in all textbooks. In the UK as well, it was in textbooks. In India, the curriculum change takes so long. So this is one of my personal effort where I would like to make a difference, because the teachers are doing their best, but they are limited by the curriculum. They need to finish the syllabus. The students have to learn what is taught in the classes, but then just learning about what is enframed inside the classroom is not enough in today's world. Today's world is not boxes. Today's world is really boxes with holes all around, and each box can go into the other. And one needs to know a little bit about everything, at least from school, and before you specialize, so that you are able to categorically look at various aspects of careers, various aspects of education, engineering, medicine, and so on. And I also want to make research in science an aspiration. Today, the aspiration is missing in terms of going for research in science, in R&D, in pure science. Science karke kya karega? Jola leke jayega, jayegi, I would say, right? But we need to make it really aspirational, that the impact that one has in engineering or in the field of medicine and so on is also due. A little humble contribution comes from blue sky research. So making it aspirational means that we need role models, and we have role models in our country, but still we need to do much more in that direction. So what I'm doing is really a drop in the ocean, and everyone who wishes to join with the NGO to do something is welcome. There's another thing that I'm trying to do is to look at various technologies that are available in the field of particle physics. You know, I spoke of hadron therapy. That is a huge application. In our country, we do not have anything of that sort. And cancer is a big burden on our country. You know that 1.5 million cases of cancer every year, and more than 50 to 70% of them die. Compare the numbers with that of COVID. Nobody speaks of them. So we need to do a lot. And a center like that will cost a huge amount, you know, like 200-300 million dollars or euros or 2,000 crore rupees. But somewhere we have to begin. And every little piece is a piece of engineering. You know, it's not only the accelerator, it's a small piece here, small valve there, magnet here, you know, O-ring there, and so on. All those are engineering challenges. So a dream would be that, you know, all engineers, budding engineers get together and then just let's do it. So these are kind of little dreams I have, but I think that for the moment, I have no idea where to begin, where to go, how to do it, and so on. So the NGO is aimed in those kind of directions.
Okay, great to learn about the initiatives of the NGO. At the end, I would like to thank you, and let us hope the young budding technocrats will contribute into Atmanirbhar Bharat.
Ji, thank you very much. Thank you, everybody. Namaskar.
Thank you.
Thank you. Bye, everyone. Bye-bye.
Hi, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Bye.
Walking alone, the streets are empty. The only thing I can see is my own silhouette. I'm getting stronger, step by step. The clock is ticking, but there's no time for regrets. I've been flying from town to town, from London to Taiwan. I've been all around the globe, trying to protect your soul. We are heroes tonight. We will fly above the sky. We are heroes tonight. Yeah. We are heroes tonight. We will fly above the sky. We are heroes tonight. Yeah. town, from London to Taiwan. I've been all around the globe trying to protect your soul.
Nightmares creep while you and me repeat. This bittersweet heat is suffocating. I'm waiting and always hesitating. Kryptonite desires set my heart afire. Heart on fire. Set my heart afire. Suffocating. I'm waiting and always hesitating. Kryptonite desires set my heart afire. Heart on fire. Set my heart afire.